introduce our speaker, Yehudit Harlavan. Yehudit is a senior researcher and the head of the division of geochemistry and environmental geology in the Geological Survey of Israel. Yehudit completed her PhD at Hebrew University at the Institute of Earth Sciences, focusing on lead isotopes in weathering problems, and her current research interests are provenance studies of siliciclastic sandstones, isogeochemistry of marine sediments offshore Israel, isogeochemistry of the Nile tributaries, and interaction between spent fuel and carbonate rocks.
So I'm Yehudit Harlavan from the Geological Survey of Israel, and I would like to introduce you to a method which I'm not sure is common knowledge for everyone. For me, I heard about it, but I didn't know a lot about it, and I think it's not being taught at usual or sedimentary courses. The method is strontium stratigraphy, and I would show you how did I implement it in 2 cases here in Israel. Now, because this is a method that is not commonly used, I would elaborate it on about the first half of this talk, and I'll explain what's the approach behind it, and then I will show you 2 cases. You're welcome to interfere anytime you want during this talk. Okay. There are 2 basic methods in earth material dating. One is numerical dating. I'm sorry for the disturbance of this. It looks wider than it should be. Okay, there are 2 basic methods in dating. One is numerical, and the other is relative. The numerical dating is well known, for example, uranium lead, rubidium strontium, samarium neodymium, and so on. And it's being done, for example, on zircons, on biotite, on earth materials that consist or at least contain some of these elements and other elements that you can actually date. The relative dating, of course, it's according to the first law of geology, stratigraphy, or the superposition law, where the deeper is the older and the younger, and the uppermost is much more younger. A different method would be a biostratigraphy, and there are a lot of methods that you can relatively date. Biostratigraphy is one of them, and for example, here I show foraminiferas that can be identified, classified, and will determine a certain age in time. Sorry. So when we have sections, we usually want to combine methods, as many as we can. Not only the one that I'm going to show you, but as many as you can. For example, if you have a strata like here, and you have on one side a fauna, you can identify the fauna, you can correlate it to other places, you can determine it, and then you can determine or assign an age for this fauna. And here you have like a sequence of fauna that shows development through time, and you can say whether it's Silurian, Jurassic, and so on. If you notice here, there are numbers, which mean, for example, the Cambrian would be 442 million years. How do you get this? This is from this part of the slide. Sometimes you have magmatic igneous rock that interfere with sediments, and then you can give you can determine the age of the sediment according to the magmatic intrusion, or even intrusion or eruption of magma, volcanoes, or whatever. For example, if you look at this sail, it is within a sediment or within a layer. If you know the age, and you can numerically know the age of this sail, then you can tell, okay, this strata is older, younger than the accepted age. The strontium isotope stratigraphy is a complementary method for dating, and it can help in places where it's hard to know, or at least to get a first notion of what is the age of this sediment or this rock. Okay, I'll probably keep doing this. And it all started from one bizarre observation. What was the observation? The observation was that strontium isotope composition, and I will explain what it is, change in the ocean, as you can see here. This is by Peterman et al. 1970, and with time. So, and why is it so bizarre? Here, I'll show you. Sorry, I'll show you the. It's in a better way. It is bizarre because the seawater composition is believed, or at least assumed, to be constant with time. What do we mean by constant with time? We mean that the whatever seawater composed of elements like chlorine, sodium, sulfate, and so on, magnesium and so on, big bicarbonate, they have a very similar, the ocean through time have very similar concentrations and even very similar ratios in between those salts. So, and if that's true, for example, look at the calcium. If calcium indeed didn't change much from the forming of like the 100 million years ago, the last 100 million years, then if calcium didn't change, why would strontium, and I did show strontium isotopic composition, should change with time? Up to this point, it was believed that it has no, it doesn't really change. And indeed, when you look at the map of the salinity of the oceans here, although you can look, you can see that there are different colors, but they don't really change much. The composition is almost the same. The concentrations are between 34 to 37 ppts, and even the ratios between salts and elements remain the same. So why would the strontium isotopic composition change, or why would strontium change at all? Well, let's see, where does the cations and the anions come to the ocean? The cations are believed to be mostly contributing to the ocean by weathering of rock on land. And here, this is a geological map of the world. So if one river drained, let's say, carbonate rocks, then it would bring mostly calcium and magnesium into the ocean. If it, for example, like in the Canadian Shield, weather mostly igneous rock, then it will bring more silica and alumina and so on. So the cations are believed to be contributed to the oceans by weathering rocks via rivers. The ions, sorry, what did I wrote here? Okay, mostly from the interior of the Earth, meaning from the mid-ocean ridge, and I will show how. So the resident time of each of the cations and ions in the oceans is determined, and the resident time is in fact how much does the element spend in the water, time it spends in the ocean water before it removes. For example, chlorine has a resident time of about 80 million years, which is a long, long period, compared to calcium, and I keep repeating about the calcium, which has resident times of about 1 million years. So we know where the element comes from, and the latest model, which tells us about how does the composition of the ocean change or not change or behave with time, is the kinetic model, which is used to explain the ocean chemistry. And in this model, the balance between the elements is much more important than the kinetic and the solubility of each of the elements in the ocean. So what they've done is just they grouped the elements according to their input and removal. For example, chlorine, The main sink in geological time is vaporite deposits like salt or HCl. And this would be controlled by tectonic. Why? Because tectonics create basins, shallow basins that vaporite can be formed in. Magnesium, sulfur, and potassium, the main input is through rivers. And again, it sinks in hydrothermal circulation through ocean crust. And so it's also been driven by tectonic activity. Calcium and sodium are more complicated, and the main input is rivers, and the removal is through calcium to sodium ion exchange, and calcium to bicarbonate regulation by calcium precipitation, which means this happens in the ocean itself. And lastly are the nutrients, like silica, phosphorus, carbon, and nitrogen, and strontium, which we are going to talk about, and the input is by rivers, and the removal is through biological activity, which later on are being buried in the ocean floor. So this would be the kinetic model and explain everything, but we are interested in strontium. We want to understand why would the strontium isotopic composition change which time. Again, the same plot. I will show you these plots again and again. And just to make sure that the people who thought about it, or the studies that first came into publication from the late 50s and from now then, they have noticed that the isotopic composition of the strontium is changed with time, but it does oscillate between two values, between 0.709, and you show what does it mean, and roughly 704. 709, or even bigger than this value, is what river brings in to the ocean. 704 and sometimes 703.5 is what is being contributed in hydrothermal activity in the ocean ridges. It comes from the mantle. That's why the value is so low. So where does strontium reside? In which minerals, and why it has to do with the ocean at all? Well, we have two strontium minerals. One is strontium, which comes from hydrothermal activity. The other one is celestite, which is associated with evaporites, but they are very rare and minor in distribution. They would not impact, and they wouldn't have any influence on strontium of the ocean at all. But in major minerals, we can find strontium as well, for example, in feldspars, in apatite, and in calcium. And by far, the most abundant and thus most influential mineral would be calcium carbonate. And that's how we associate strontium to calcium, to the ocean through calcium. Now look at the periodic table. What you see here is that calcium and strontium belong both to the earth metals, and they behave the same geochemically. They have the same ion radius, and they have the same valence, +2. So they have almost the same size, so they can substitute for each other. Strontium substitutes for calcium because in most cases calcium in the tens of percents, while strontium is in ppms and ppbs. So usually strontium will substitute for calcium. And how much it substitutes, it depends on the partition coefficient. And this has to do with the type of mineral and so on. So every time we have calcium in mineral, we will have strontium as well, if strontium exists in the solution that precipitated the calcium. And it usually does. So if strontium can substitute for calcium, then we can use the strontium isotopic composition to learn a lot of things. Now, what is the strontium isotopic system, radiometric system? That's a system that is being used for numerical dating. How many million years, usually, this earth material how old is it? And it's based on a very simple radioactive decay of rubidium-87 to strontium-87. And then we have a beta as well. So this decay is spontaneous, is independent, and the decay constant is very, very long. So we have this decay which produces strontium-87 from rubidium. Strontium-86 is not a decay product. And if we look on rubidium and strontium on the same periodic table, you can see that they are both belong to a different elemental group. The rubidium is an alkali metal, while, as we said, strontium is earth metals. This means that they behave geochemically different. So in each earth material, in each mineral, in each rock, the rubidium to strontium may change. It's not constant. The ratio of rubidium to strontium in earth materials is not constant, it's changed. And if this change, then the strontium-strontium isotopic ratio will also vary. Why? Because if you have rubidium, then it will decay to strontium-87. So this ratio will also change. And if you don't have rubidium in your sample, then the strontium-strontium would be lower and different. So this is the whole idea. So we go back to strontium in the ocean. What is the mass balance of strontium in the ocean? It's quite simple. We have river influx into the ocean with a ratio of 0.711. It's like a DNA fingerprint. This ratio is very high because the weathering of rock, of crustal rock on land, will produce high ratio, because crustal or igneous and magmatic rocks have a high rubidium to strontium ratio, meaning that rubidium will decay to strontium and the ratio will be higher. So this is the river flux. We have the second one, the second source, which is the hydrothermal exchange in the ocean ridge. This is like a schematic of the ocean ridge, of the floor on the ocean floors. And here you have circulating water with the mantle below. And the mantle has a ratio of 0.703. This is a crust value, and this is a mantle value. So you have very different values that comes into the ocean, almost the same magnitude. And we also have carbonate recrystallization, which will cause this carbonate in this day to copy or to record the exact strontium of the ocean. Since the ocean today are 0.709, the seawater in the ocean, seawater strontium, then the carbonate will be 709. So we have this three contribution. So basically, we have a long resident time of of strontium in the ocean, some 2.5 million years. And we know that the ocean mixing is about 1,000 years, which means that that strontium in the ocean is well mixed. And the strontium-strontium ratio in seawater is homogeneous. Nowadays, if I'll go everywhere in the world, in the oceans, if I stay a bit away from big river mouths like the Nile or Amazonas or whatever, I will get the same strontium isotopic composition of the seawater. It is well mixed, not like maybe not like neodymium, for example. And so strontium is very good in that matter. And just a moment. So if we look on the equation, a very simple equation, what we measure in seawater is a combination of three sources, at least three sources, which has each their own fraction. One is the old crust that can get up to 720, young volcanics of 704, and carbonate of 708. So why would the isotopic composition of the seawater change with time? Which of the ratio can be, which of the fraction of each ratio, like S, V, and M, is likely to change. You have an idea? Caught you by surprise. Well, the changes are mostly due to the weathering that happens on Earth, on land. Mostly this ratio change, or the the flux of this ratio, the amount and the isotopic composition of the crust, weathered crust, can change. For example, if you raise the Himalaya all of a sudden 40 million years ago, and you expose huge ridge to weathering, very old rocks, you would get a very old ratios, which means that this ratio is higher. So that's what changed, and that's what happens with time. And just a moment, and studies, people who want to study organisms or big tectonic events happening on land, they would go to the strong isotopic composition of the ocean and see when and exactly how it was recorded. So it's you wouldn't think that something like that would affect tectonic studies, but it does. So Foraminifera, they live in the ocean, and they have streaming granular like that you see here. This is an alive Foraminifera. We just took it from the internet, which they use to catch food and other uses. And they commonly have external shell that you can see here. We call it test, which has diverse forms and material and so on. What's important is that the test or the shell have either one or more chambers, and they are commonly built from calcium carbonate. And hence, this is how we get to strontium. When this forum today built its test in the ocean, it doesn't really matter. It doesn't really think of us wanting to study the strontium within. While building the test for calcium carbonate, because of the coefficient partition, it will also incorporate strontium in its test. And that's what we aim to. So that's the whole basics for the method. So Foraminifera preserve the seawater record. And for example, this Foraminifera from the Jurassic-Trias period. And he grew up here. He grew up in the water. He recorded the strong isotopic composition of the water at this stage, at this time. So if I'll get a handle on it and I'll analyze it, I will be able to determine the age. Will be able to determine what was the isotopic composition of the seawater. So in this curve, you can either use it to build it. I mean, you can either add data to this curve, and I will tell you how much data are on this curve, or you can use it the other way around. You can analyze the strong isotopic composition of foraminifera that you found in a sediment and try and determine the age. Now, what's the problem? That if, for example, I determine the age of this foraminifera to be 708, let's say 3, I have many places that this line transects the global curve, isn't it? So how would I know? Maybe it's very young, fresh air, and maybe it's very old up here. So you never take one sample, and I will show you how. So do you remember telling you about the fact that Himalaya rose somewhere here? From the start, this event of the collision of India and the Tibetan plates, we start getting a very highly radiogenic strontium into the ocean, and there is a huge decrease, a sharp decrease in the strontium isotopic composition to this day. And we also see it somewhere here even earlier, for example, for the Pan-African organism. So this is the basic. So Sr Isotope Stratigraphy methods relies on the fact that the strontium isotopic ratio of dissolved strontium in the world ocean has varied over time. If it was constant, we wouldn't be able to use it. It uses the plot of strontium ratio with time, and this plot composed of about 4,200 pairs of isotopic ratio, which has a very good age. And that's how it was constructed. So what we do, we compare the measured strontium isotopic composition that we measure to the above curve. And then we can assign a numerical age. This is not rubidium strontium or geometric dating. We do not measure the decay of rubidium to strontium. We just use this curve that has to do with tectonics and hydrothermal activity in the ocean and was recorded by Foraminiferas to assign numerical age. So what are the best candidates? Fauna that build their test from calcium carbonate, because if you take, for example, radiolarias that build a test from silica, it wouldn't be good because silica would not incorporate strontium in the lattice. Live in the water column. We don't like those who live in the sediments because they are subjected to other processes that may alter the strontium isotopic composition. So we like them when they are planktonic. They just swim in the ocean and they build their test while doing so. And at the end, most important is they exhibit no diagenetic alteration or growth, and there's no sediment filling. All these things are very, very important in order to assign a numerical age. So again, we look at the same plot. This is the most comprehensive plot exists for today. It is it calls the lowest fit. It has more than 4,000 pairs. And one thing I want to show you is that you have a very good data sets here with a narrow error or narrow band of error. And then as you go further back in time, then you get less and less data, simply because it's very hard for earth material to preserve to be intact for so long. As time goes by, it is subjected to alteration, to diagenetic, to dissolution, and so on. So we have a very good knowledge of the first part and less. And this part is also being constantly rebuilt or reconstructed. I would not go to you how this curve was built. But what I want to emphasize is also that for each period, the fauna that is being used is different. Not because we choose a different fauna, but because this is what we have. This is what we have to work with. So the neogen is really, really nice, and it has a foraminifera of calcite and on the DSP sites and drills. So there's no fauna, there's no problem. But if you go down to the Cambrian age, there's it is more problematic, and it's still being, for example, trilobites are being used, which also build their tests or shells or whatever, hard parts from calcite, but it's more challenging to do it. So how does it work? As I told you, if you get a certain number, then there are many options for it to yield an age. So you never do it on one single data point. You do it on a set of data points. And as you can see here, there's a negative and positive slopes here. The degree of slope changes, so you can use that. Here's an example. If you have a section here which has very nice foraminiferas all along, very set, and no problem with it. Then you analyze for, let's say, four points along this section. As you can see here, these 4 lines. And you want to correlate section A with section B. One section has a fossil, and the other may have other fossils or none, or not indicative fossils. And the correlation uses all 4 numbers. All 4 numbers should create the slope, the trend of it, if it's negative or positive with time, and it will allow you to correlate this section to this one. I mean, this one is the lacking one, so it will be correlated to the one that that exists. So the slope, yes, at this part is the same. And if you have the slope, then you can determine the sedimentation rate and so on. So this is how it's being done. And also, of course, you keep relying on the fact that this point should be older than this one, merely because of the superposition stratigraphy. Let's take very, very shortly, let's see what happens when we have a constant rate of sedimentation. Let's look at number 1. This is what's supposed to be the change with time of strontium isotopic composition. This is your samples. They have the same slope, so there's no problem of determining it. If you have a slope that jumps in one place, so there's no sedimentation in this part. If you have 2 pieces of slope, 2 pieces of sediment sections that have the same slope, but and there's a missing inside within, then simply this period there's no sedimentation rate. Here, for example, if you have a certain slope and then it slows down, so or even steeper, then it reflects on the sedimentation rate, whether it was slowed or increased. And a plateau interval means that the sedimentation was preserved. It is more difficult when if you have this scenario when there's varying sedimentation rates, which usually happens, then it's more, if you have the same change, then you have no problem. But if you don't have the same change, then it's much more difficult to comprehend. So when is this most useful? If you have numerical ages from different sources, then it's less useful. If you have a very good fauna, then it's less useful. But it's very useful when there's fauna, when the fauna is not well preserved, or the fauna consists of specimens that do not indicate a certain age, when there's missing sediments, or there's no fauna at all, and correlation of sections that otherwise are hard to correlate. And we have many of these all over the world. So final note, special care and treatment should be taken when you do this methodology. So the first sample the first case I'm going to show is from Nitzan Mizrahi master, which is just completed, and it's based on work that by Ari sitting here. And this has to do with a section in the Shfela, near the area of Adert. It's a place here. And it consists of oil shale deposits in a big basin that we call Shfela. This basin has sediments that were supposed to somewhere deposited between the KT boundary, which has this ratio of strontium isotopic composition, and the upper Sannonian, which has this ratio. And that is the slope or the change between these 2 points in time. How do we use this? So first we take Ari's work, And I just highlighted this section. In the red part, he has ages. In the blue one, he has the stratigraphy. And most important is the green box. So first, you determine the biozones, which are based on the first and the last appearance of indicative fauna, like you see those arrows. And then you assign an age by referring to other studies. But due to hiatus, the first and last appearance may be missing. It's not always there. So dating this type of section could be challenging. But we took this section because we knew it was well described, and we have ages on this, and we wanted to know how good is the method that we've used. So I came into this work quite late, and by that time, specimens were collected for biostratigraphy. This was done by Nitzan. The problem is that he didn't collect only planktonic foraminifera, he also collected benthonic as well. And since he only wanted to identify this specimen, he didn't care whether they are filled, altered, or whatever. And we said that these processes can change the isotopic composition and will hinder our understanding on the time it was created. The foraminifera precipitate its test. So specimens were collected. Some 30 milligrams were dissolved using acetic acid for 10 minutes. Solution was analyzed for major and strontium concentration, and the isotopic ratio was determined. This is only one plate of sample of sediment. About 300 or even 200 specimens were collected for each analysis. Luckily, it wasn't me that collected them. I wouldn't know how to do it. So Nitzan had done this work, and also he analyzed the isotopic composition of strontium in these samples. So here we show the strontium isotopic composition of all the samples that were collected. You see there's more than 100 here, by versus depth. We have no idea what the age is now, but we do know that this sample is younger than this one, because this was taken from 240 meters below surface, and this was taken from about 540 meters below surface. What can we immediately notice is the samples here, two samples that are younger than the KT boundary. So we just threw them away. Also, we can see that there's a nonlinear behavior here, which also is a very problematic, but otherwise, even if you consider the large error on the isotopic ratio, it does show a good linear array, and although a bit scattered. So we threw these samples, as I told you, and we can notice two linear arrays through this data set that almost have the same slope. For this one, we are quite sure, but for this one, it may be regarded differently in terms of where exactly is the line. So if I place the curve of the global change in the strontium isotopic composition with time on this plot for the certain time we have determined, we can actually see that there's a good match, and we can determine ages on several places along this plot. So we did that, and when we compared the ages that were referred to or assigned using other people, using Ari's work, and using the known ages for these biozones that he identified, then we can see that there's a million and a half year gap between the two possibilities. For example, in 452, somewhere here, we get 70.7 million years by Ari, and versus 72.5 by this method, and so on. So as I told you, this was our first work, so we didn't really pick the specimen well as we should have, because this wasn't the main aim of the study by Nitzan. So what are the problems? Do we deal with filling? I mean, if you have filling within the chambers of the Foraminifera, then the filling is much younger. So it will give a mixture between the filling and the test would give you a younger age eventually. Is it diagenetic? Some of the tests were dissolved, replaced, or altered. Is it mixing between two end members? Maybe we weren't careful enough, and detritus also interfered with our samples? Or is it the type of fauna, benthic versus planktonic? I think that almost all the options are right. Let's see, this is from Sass et al., 2009, who worked on the same section. And he showed that in spot A, there is a diagenetic calcite, which almost mimic or perfectly mimic the cell form, but it's a diagenic one. And also you can see here in B, there's this cubic shape, almost cubic shape, because calcite doesn't have a cubic shape. Here, growth of calcite crystal. These two options also can change slightly the stromistopic composition that you get. What about the mixing of two end member? It is very common to plot strontium's ratio versus 1 over strontium to find out whether we have two end members mixture. And as you can see here, there's no correlation, there's no linear array, which means there's no mixture. We were able, indeed, to analyze only the calcium carbonate in this rock of the fauna, but we are still dealing with some filling or diagenetic events. So a second sample was the Triassic-Jurassic transition. This work is done with the Dorit Korngreen. This is how this method is really, really helpful, because first of all, we have no exposure of this section. During the Triassic to Jurassic transition, there was a mass extension. It's not exposed in Israel. So we don't know exactly where the Triassic-Jurassic mass extension appeared in Israel. So we took one of the boreholes, we analyzed 3. I'm going to show you only the Elija Borehole that was drilled into this transition, and it was believed that the transition itself is missing in Israel. Not that we don't see it, but it's also missing because of a big hiatus in the geological history of Israel. So we took the Elija Borehole, but we had a problem. We didn't get a nice core that was taken. We had what we call cuttings. Cuttings means that you just you drill, and you throw out pieces of rocks. Now, these pieces of rock it was estimated that it represents plus minus 3 meters, so it's really a problem. Also, there's almost no fauna, and that exists has a very bad preservation. And also, this section or this part of the geological of the history of Israel is associated with hundreds of meters of volcanism, which also can hinder or can makes interpreting very challenging. And massive volcanic, that's what it was important to us, was believed to be part or maybe one of the reasons for these Triassic to Jurassic mass extension, transition mass extension. Why? Because it would release CO2 and then cause global warming. At the same time, it can release sulfate, which can go global cooling, but we're not dealing with it. This is not our problem. We just wanted to see where does the transition appear and how does it relate to the volcanism that we can see in the section. So these are the results. Again, we have a big arrows on the isotopic composition only because it represents 3 meters, each sample here. So they can mix still. You can see a very nice correlation of a slope, and I will show you how it relates to time. And we have two not problems, but 2 distinct groups. One is this one that show no relationship to age or other elements that we already also analyzed, and we have also this one. If I superimpose the curve, the global curve, you can see that it fits well, and the Jurassic to Triassic boundary is here. Just before, if we go deeper, we get to this set of samples. So we have the boundary. We do record the boundary, and the edges fits quite well. Even though we didn't do it on fauna, we had a large error because of the type of drilling. We can't see it in eyes because it is well in the depth, and we have no exposure on land. So this really had a very huge add value for the geological history of Israel. Now let's see it on a combined sketch. It's the same Elija Borehole. Just a moment, please. Here you have the Triassic-Jurassic transition. This is the red line. See you. In terms of lithology, we have the volcanic hundreds of meters. Look, associated with dolomites and other rocks, but we have almost 1,000 meters of volcanic. We have dolomites on top of them. We have the fauna that was hardly found, places above, some places a bit below, mainly riffle fauna, and we have the isotopic composition of strontium. And as you can see, all these samples has a volcanic effect, and they correlate very well to the volcanic sequence here. This is carbonatic sediments within the volcanic. So we were able to numerically date them, and you can see that they are associated, and they are affected by the volcanism itself. And at least for Israel, you can see that the volcanism is associated with this transition of Jurassic to Triassic mass extinction, as you can see here. This we interpret as caving, which means when an organism cave, or it's just mixed sediment, and it's of course cause problems. But overall, we have a nice behavior with time of the storm isotopic composition, and this is where you should imply this methodology when you have no other choices. And there are so many places, at least in Israel, that are known to have no. We know that this is Meilijson age. We know exactly, but there are many dispute. There's a lot of dispute around these sections, and this method should be used. So overall, conclusions are very simple. This is a complementary method when there is no fauna or there is a wide hiatus. One needs to carefully choose the fauna, not like we did. Well, it wasn't aimed to, but more carefully than we did for the first set of the first case I've shown you. One needs to avoid tests which have filling or recrystallization. Just avoid it. Today we can analyze very small samples, so there's no point of collecting everything you see. Just choose what you collect or handpick, and special treatment of the sample is needed. That's it. Thank you.